In this video, we're going to take a look at Kruskal's algorithm. So the actual implementation of Kruskal's algorithm is generally going to start off with us setting up a graph, right? And our graph is going to be a little bit different from the ones that we've set up in previous videos. The main difference being that we're going to want to keep track of the number of vertices that we have inside of our graph, and that our adjacency is going to involve weights and edges now, so we have to account for that. So we'll take a look at how we can do both of those pieces. So for the vertices, we just store them inside of a property, and we'll provide them as a constructor for the actual object itself. And then with add edges, basically all we need to do is provide in the starting point of the edge, the ending point of the edge, and then the weight of the edge itself. And then what I'm going to do is I'm just going to append that into my adjacency list exactly that way. So UV and the W, which is the weight between those two edges. Now, another thing we're going to need to do is be able to determine if a graph contains a cycle. I'm going to show you some interesting efficiency gains that we can get out of our previous cycle finding algorithm. And generally, all we need to do is just define our find parent in union to start. So the idea of our find parent is still the same, where we're going to look inside of the list to determine what the parent of the current item is, and then return back that parent. And we can use that to determine if there's a cycle. If two things have the same parent, they must be in the same set, and therefore it is a cycle, right? What I'm going to change here is something that is going to allow us to do an efficiency gain known as path compression. Basically, if the thing isn't the parent, what I'm going to do is I'm going to set the parent at I equal to the result of find parent, parent, parent at I. This is called path compression. So basically what we're doing is we're saying if something isn't its own parent, right? So if we're not currently at the parent, then we move that thing up in the tree. And you can see that as like compressing the distance between our nodes and the actual root of the tree itself. So that's the idea, is that we're just trying to move ourselves a bit further up inside of the tree. So we could do this and then say return parent at I. This just allows us to keep our checks as efficient as possible. Then we're going to see a second efficiency inside of our union. So our union is going to take in a new argument, which is called a rank. You can think of the rank as similar to the height or depth of a tree. It's basically telling us how large that tree generally is. And the idea is that before I set one tree to be underneath the other, I want to determine what the height of those trees are. So for instance, if the rank of X is less than the rank of Y, then I'm going to put X equal to Y. So do you see how I'm going to set that based on the actual rank that's being set here? So I'm actually going to move things based on the rank because I want to make sure that the paths stay as small as possible. So I want to make sure that I'm moving things in a way that, is conforming to that idea. So similarly, if rank of X is greater than rank of Y, well, then we should do the opposite. We should say that parent at Y is equal to X. And then if they're equal to each other, basically all I'll do is I'll say that the parent of Y is equal to X. And then I'll say that rank of X is incremented by 1. And that's all there is to it. So we do this because with Kruskals, it really depends on these operations. These operations are very important. So I want to make sure that these operations are done as efficiently as possible. So I'm implementing the best possible option, whereas before we just kind of implemented ones that worked well enough for us. From here, we'll actually implement Kruskal's algorithm. Kruskal's algorithm starts by creating a result, which is going to be the minimum spanning tree that is created. We're then going to keep track of two things, basically. The number of edges that we've picked out of the graph and the current vertex that we're at. The current vertex that we're at is going to be I, so this one is the current vertex. And this one is going to be number of edges picked, right? From here, I'm going to sort my adjacency list so that it stores from smallest to largest. I'm going to do this using the built-in Python sorting function. Main reason for that is that it allows me to set up which index of an array I want to sort by. In this case, I want to sort by the weight, right? So I'm saying item at 2, which is the weight, right? The item at index 2. So that's what I'm sorting by. So it's going to sort us by weight smallest to largest. The other reason why I'm using this sorting algorithm that's given to us by Python is because it's not really the point for me to show you like a sorting algorithm in this example. I want to really focus on Kruskals. So we're just saying, we're going to sort it in some sort of way, preferably the best possible way that we can. And then we're going to do Kruskals algorithm. So this just sorts the data that we want to use. Then I initialize my parent. I'm going to start by doing something like this, just to create a number of entries for each of the vertices inside of my graph. I'm then going to set up an array for my rank. And then what I'm going to say is I'm going to say for j in range of self.v, we're going to set up parent at j to be equal to j. So similar sort of idea, we give them each their own disjoint set. I'm going to append a rank of 0. Since they're all in their own disjoint set, every single tree that we have has a rank of 0, right? It's just the root element. And then we actually do the main idea of Kruskal's algorithm, which is to say, while the number of edges is less than self.v minus 1. The reason why that's our stopping condition is because in a tree, we would have at most vertices minus 1 edges inside of it. That's one of the properties of a tree. So this is a good stopping condition for our particular implementation of Kruskal's. From here, I'm going to pick out the different edges that I have out of my adjacency list. So I take my current edge that I have, which remember is going to be the smallest one because it's sort of from smallest to largest in weight, right? I then check to see if they are a part of the same disjoint set. And I just do that by finding the parent of each of my nodes. If they are not a part of the same disjoint set, it means that a cycle won't be formed. So that means I can pick this edge, so I increment e by 1. Or I guess e, plus equals 1, right? Let's just keep that consistent here. There we go. And then what I could do is I could append to the result the edge that I've picked, since that will be a part of my minimum spanning tree. And then what I'll do is I'll just go ahead and union together those two sets that I have based on the rank. That's all there is to it. We just pick the minimum edge that doesn't create a cycle, and we're good to go. At the end here, something that I like to do is I like to calculate the minimum cost. It's just nice to be able to do this, since that's really one of the main points of this algorithm. We can do that just using this sort of structure here. We just say minimum cost plus equals w. Just like that, right? Then from here, what we could do is we could just return back the minimum cost and the results. I like to return them just inside of an array like this, right? And there we have got it. Well, yeah, so we would say minimum cost, sorry, and result, right? Just like this. Now I can see that this is giving me an error, I think just because I haven't indented it. Yeah, there we go. Just had the wrong indentation. So now we're good here. So let's take a look at an example and see if this actually works, right? I'm going to create a graph with 3 vertices, and what I'm going to do is I'm going to create a few different edges. I'm going to have an edge from 0 to 1 with a weight of 5. Let's create an edge from 1 to 2 with a weight of 7. And let's create an edge from 0 to 2 with a weight of 10. Let's take a look at what ends up getting picked out of these, right? So I'm going to do a print of g.Kruskal, and we can take a look at our result. You can see here that the optimal weight is 12, which is taking the edge 0 to 1 and 1 to 2, right? Which gives us a total weight of 12. And we know that this is actually making decisions because it could have gone 0, 1, 0, 2, which would have given us a weight of 15. That would have been bigger, right? So you can see that it actually does give us the minimum spanning tree in this case. So this is our implementation of Kruskal's algorithm. The final sort of piece that we really need here is what ends up being the time complexity of this. And the time complexity of this is going to look something like this. It's going to be O of E times log of E. Basically, we have to iterate through, at worst case, all of the different edges that are inside of our graph, right? And generally, these union find parent operations are going to have some time complexity to them. Since we've balanced out these trees fairly well, they should maintain about a log of E time complexity. So this is how we get the time complexity of our implementation of Kruskal's algorithm. So this gives you one way of finding a minimum spanning tree. In the next video, we're going to take a look at Prim's algorithm, which is a different approach for finding the minimum spanning tree inside of a graph. So thanks so much for watching, and I'll see you in the next video.